Hello, in this video I'm going to discuss some physics terminology because when you start learning a new subject, and physics is no exception, you get bombarded with terminology. It can be very confusing. Now I can't go through everything here because that would take forever. There's loads of physics terminology, but I picked out 4 things that I think are particularly useful because they can help you to structure your thinking while you're learning physics. The first piece of terminology that I'm going to consider is a distinction between classical physics and modern physics. So science as we know it nowadays is a relatively recent endeavour. So this is science where descriptions are based on observations, controlled observations of the world, using scientific experiments. So this came in say, the 15th or 16th century. Before then, we had what we now refer to as natural philosophy, where they were creating descriptions of the world that weren't based on these controlled scientific experiments. So those earlier descriptions, those descriptions of natural philosophy, were often mistaken and based on a biased view of the world. So when science as we know it now came into being, that was the advent of what we refer to as classical physics. So classical physics ran from, say, the start of science in the 15th or 16th centuries through to the beginning of the early 20th century. And you had scientists such as Galileo and Newton and Gauss and Faraday, and they were creating descriptions of all the major phenomena of physics, motion, forces, light waves, energy, things like that. So they created all of these descriptions, and this is all part of classical physics. But then things started to unravel. We were getting a lot of observations of the world at the end of the 19th century and the beginning of the 20th century that was suggesting that these descriptions of classical physics were wrong. They weren't as accurate as they could be. And then at the beginning of the 20th century, or at least in the first 20 years or so of the 20th century, there were a lot of groundbreaking discoveries in physics, and that brought in the era of modern physics. So we're talking about the work of Einstein and Fermi and Dirac and Pauli and Schrödinger in things such as relativity and quantum mechanics and particle physics. So this was a whole new load of descriptions of the world that were more accurate than the old descriptions. And the changes were so big that we now describe these 2 eras as classical physics and then modern physics. So modern physics is the more accurate stuff, but that doesn't mean to say that classical physics is useless. It's still very accurate in a lot of situations. So usually situations that don't have great extremes in them. So if we've got extreme velocities, things are moving really, really, really quickly, then we need relativity, which is part of modern physics. If we've got extremely small things, then we need quantum mechanics, which again is part of modern physics. But if we don't have those extremes, then classical physics is still great. It's still very accurate, and it's still very useful to learn, which is why when you start learning physics, pretty much everything you do is in classical physics. It's still extremely useful, and it is easier to learn. But it's worth keeping in mind when you're going through physics, what is part of classical physics and what is part of modern physics, because it will tell you when the theories that you're learning are applicable. So you'll know the limitations of the things that you're learning, and it points you in the direction of where you'll go in the future for future learning in order to get those more accurate descriptions. Okay, the next distinction is between macroscopic and microscopic. Right, so macroscopic, we're looking at large scale and aggregated, versus microscopic being small scale and individual. Right, so let's delve into that a little bit more. Macroscopic, large scale. So when I'm saying it's large scale, that doesn't necessarily mean huge. An egg would be macroscopic. It's not, an egg isn't enormous, but it's big compared to, or very big compared to an atom. So I think the more useful way of looking at it is this idea of things being aggregated. So if we were, say we were going to throw an egg through the air and look at its motion, we're not looking at the motion of every atom in the egg. We're looking at the motion of the aggregation of the atoms into the egg. So we're looking at the scale of the egg. We're not looking at anything smaller. So it's macroscopic because we've aggregated up all of the small things, said, right, we're going to look at it at a larger scale. Another example might be if we were going to measure the temperature of a swimming pool. We go along and we look at all of the water in the pool, and we want to measure the temperature of that. We want to aggregate up all of the water molecules into the macroscopic description of the water as a whole. So we've got all of the water in the pool. We'll make that large scale. We're going to look at the level of the swimming pool. We're not going to look at the level of the individual water molecules. So it's this idea of aggregation. And that's different to if we're at a microscopic scale. So if we're at a smaller scale, typically things that we can't see, because we're breaking down and looking at individual atoms, individual particles, molecules, particle just being a general word for describing either, say, a molecule or an atom. We don't care specifically what it is. It's just something, a particle is something very small that we're considering on that small scale, and we're considering it individually. So if you were going to look at a gas, so gases is a common one. We'll look at that in physics later on. Do you want to look at it at the microscopic level of what are all the individual particles in the gas doing? How are they moving around? How do they behave when they bash against the wall or the side of a container that they're in? If you want that microscopic description, or do you want a macroscopic description where we're looking at the gas as a whole? We're aggregating up all of the particles and saying, okay, well, this is the pressure of the gas, this is the temperature of the gas. So we're not looking at the individual particles, we're looking macroscopically at the gas as a whole. So you'll see that macroscopic and microscopic come up a lot in descriptions throughout physics. So think of them both in terms of scale and in terms of aggregation. The third piece of terminology I'm going to consider is another distinction, this time between theoretical and operational definitions. So when we're creating these descriptions of the world, which as we know is the primary objective of physics, we need to put in a lot of definitions. We need to say what things are. What is energy, what is force, what is mass, what is weight. So we need to define things. And there are two different ways we can do this, because defining things is not easy. So we've got a theoretical definition, which is a way of understanding the cause of a particular phenomenon. So, for example, if you wanted a theoretical definition of weight, then we could say that the weight of an object is the force experienced by that object when it's placed in a gravitational field. So that definition has to be rooted in a theory of what force is and what gravity is. So it's built around theories. You can see that in the name, is a theoretical definition. But we don't have to define things that way, because theories are often complicated, they're often uncertain, and they're often confusing. And sometimes we can make a lot of progress by looking at an operational definition, which is based on a way of measuring a particular phenomenon. So it's based on an action of measurement. So to continue the example of weight, we could say, well, actually, the weight of an object is the measurement recorded when that object is placed on a set of scales. So it allows us to say what weight is. It's something that we measure, and that's how we measure it. But it doesn't tie ourselves to theories of force and gravitation and things that are more complicated and maybe unnecessary for what we're trying to achieve, maybe more uncertain. So we've got two different ways of looking at things, and we'll see that as much as people often think that all of our definitions, oh yeah, we want everything to be theoretically based, we want to have descriptions of understanding for everything that we're looking at. There's a lot of things that we really don't do that for. We're quite happy to measure time with a clock without thinking too much about what time actually means. We're going to spend probably years of learning physics when you get started without thinking about time at all beyond it's something that I've measured using a stopwatch. So don't knock operational definitions, because they're very useful and they can take us a long way without getting us sidetracked and going off in tangents and getting bogged down in stuff that might just be clouding the issue. And now the fourth and final piece of terminology is the idea of per and per unit. So this comes up all the time. Physicists and, well, all scientists really are using per all over the place. So yeah, we hear meters per second, revolutions per minute, miles per hour. So per is just it's a quick way of saying for each. It's describing how something is divided up. So if we're saying 10 meters per second, then we've got 10 meters for each second. So for each second we have, something has moved 10 meters. It's describing how we're dividing something up. So if we were going to then say, oh yeah, something's moved 100 meters in 5 seconds at a constant velocity, then we can say, well, 100 meters in 5 seconds, well, we divide that up, 20 meters for each second, 20 meters per second. It's just describing how we divide things up. Now, usually people are okay with per. It's per unit that throws people. The adding unit in is just giving us a more flexible version of per, because we don't always know what blocks we're dividing something up into. So when I was saying that, oh yeah, we've moved 100 meters in 5 seconds, so it's 20 meters per second. Well, what if we weren't using seconds? Seconds is our unit. So we could just say, well, per unit is detaching that division, is detaching it from the idea of seconds, because we might have said, well, actually, we don't want to do seconds, we want to do milliseconds. But we can still give a description. We can say that the velocity is the distance traveled per unit time. So now we can apply that to our 100 meters. So we've got 100 meters is the distance traveled. But if we're going per unit time, well, instead of having seconds, we could have milliseconds, in which case it's gone 5,000 milliseconds. So we can then say, well, we've got 100 meters divided by 5,000, and then we've got meters per millisecond rather than meters per second. All we've done is change the unit from seconds to milliseconds, but we haven't changed the actual definition of what it is that we're working out, what velocity is. It's still distance per unit time. This is how we can change between, say, meters per second, miles per hour, kilometers per hour. They're all velocities, but we're just changing the units around by having this per unit in the definition. And then we pick the unit that we want when we actually calculate a particular value. So it's just a flexible version of using per. And that concludes the 4 pieces of terminology that will come up time and time again. So yeah, if you feel as though you're getting confused by any of these in future, you can always come back to this video or give it a little bit more thought. Because if you've got these 4 things in your mind, it will really help a lot in structuring your learning.